Here we have a horizontal beam whose weight we know it's 1,000 newtons. And we have a person whose weight is 500 newtons. So we know the force, at least some of the forces here. And we're assuming the person is able to move further away from the wall. And we want to know what's going on with the tension in the rope. So first of all, if we want to figure out how does the tension in the rope change as the person moves, what would be a good object to analyze here? What's probably the single object that would be most useful to focus on?
Like that pivot point or next to the person?
Well, the pivot point is just one single location, but what object is it attached to that might be useful to analyze here?
Oh, analyzing the beam.
Yeah, I would focus on that beam itself, largely because that beam has lots and lots of forces acting on it. In particular, it has some forces we know, and also it has a force we're trying to figure out more information about, the tension on the cable itself. So the tension of the cable, that's the force of the pull of the cable on both the wall and the beam itself, because everything that the cable is attached to is experiencing that tension. So if we start by drawing out a free body diagram for the beam, or rather an extended free body diagram, because I think torque is going to make a difference here. So we should consider where the forces are, not just how strong they are. So considering the beam itself, we've got this beam, which we can treat as just a horizontal bar. What forces are acting on that beam?
Gravity at the center of mass.
Yeah, gravity is pulling the beam straight down at the center. And how strong is that force?
At 1,000 newtons.
Yeah, 1,000 newtons. Yeah, gravity is pulling the beam down with 1,000 newtons. If we knew the mass of the beam, we would have to multiply that by g, the gravitational acceleration. But this actually tells us the weight. 1,000 newtons is already a force. And yeah, the person as well. The person is applying a force to the beam. And how strong is the force of the person on the beam?
$500 newtons.
Right. The person standing on the beam is pushing down with a force of 500 newtons. So I'll call that F sub P for force of the person. By the way, what kind of force would we classify that as? I mean, here we're just labeling it as force from the person on the beam, but what kind of force is it?
Like a force of gravity?
It's not directly a force of gravity. Force of gravity we already took into account. Gravity, the Earth's gravity is pulling the beam down with a force of 1,000 newtons. The force of the person here is not the person's gravity pulling the beam. Strictly speaking, the person's gravity would pull the beam up with an extremely weak force because the person's mass is so small compared to the Earth. But this is really the force of the person's feet pushing down on the beam. That's not gravity. What do we call a force of two objects in contact pushing on each other like that?
Normal force or contact force?
Yeah, I would actually go ahead and call this a normal force here, which is one example of a contact force. Contact force means any force that acts when objects are in contact with each other and doesn't apply if the objects are not in contact. This one is specifically a normal force because you've got the surface of the person's foot in contact with the surface of the beam, and you get a force perpendicular to that surface, perpendicular to the surface of contact. So this is a normal force. The beam is holding the person up by applying an upwards normal force. The person is pushing down on the beam, which we would also call a normal force. Normal, again, just meaning perpendicular to the surface. So this is the normal force from the person's feet on the beam, and the strength of that is 500 newtons. And how can we tell it's 500 newtons, by the way? Why would the person's force on the beam be 500 newtons? What force is actually given as 500 newtons in this problem?
The weight.
Yeah, the weight of the person. And that is force of gravity. The weight of the person is the force of gravity on the person. But we wouldn't include force of gravity on the person in this diagram because we're just looking at the forces on the beam. But if we separately draw out a free body diagram for the person, and I think with the person we can just treat as a single point because the person is fairly small compared to the other distances involved. So let's say the person we just treat as a single point. What forces are acting on the person?
Gravity and then the force from the beam on the person.
Yeah, we've got gravity pulling presumably straight down. And how strong is the force of gravity on the person?
500 newtons.
Yeah, that's actually the given information. And let me label these in a little more detail. Force of gravity on the person. In fact, that's the force of Earth on the person. Gravitational force of Earth on the person, 500 newtons straight down. But how do we know there has to be another force involved here?
Because the person isn't moving. They're
Right.
not falling.
Exactly. If the force of gravity was the only force involved, then the person would be accelerating downwards, free fall. Since that's not happening, there's no acceleration going on. We know, what does that tell us about all the forces on the person?
They add up to 0.
Right. So there's got to be at least one more force. And in this case, there is just one more force from what other object?
The beam.
Right. So this other force would be the force of the normal force of the beam on the person. And that'll also have to be 500 newtons because the sum of the forces is 0. So this is ultimately because of Newton's first law. The forces have to add up to 0 because the person is not accelerating. So the other force, the force from the beam on the person, has to balance out the given force of gravity. So drawing out the free body diagram for the person can help us with the free body diagram for the beam. It's not strictly necessary, but it can be a useful way of figuring out why this has to be true. Specifically, if the beam is pushing up on the person with 500 newtons, what else is happening? What other force is guaranteed by the force of the beam on the person?
The force of the person on the beam.
Right. If the beam is exerting an upward force on the person, then the person is also exerting a downward force on the beam. So these two forces are the pair of equal and opposite forces that Newton's third law is talking about. The force of the beam on the person and the force of the person on the beam. Those two forces are essentially the same force viewed from two different perspectives. The beam pushes the person up with 500 newtons and the person pushes the beam downwards with 500 newtons. One interaction that involves two objects. So the free body diagram for the person, not really necessary as part of this problem, but it can be useful for figuring out why the person has to exert a force on the beam and how much and in which direction. If the whole situation was accelerating, then that would make a difference. We would have these forces not add up to 0. Instead, what would they have to add up to? If this whole system is accelerating, what would these have to add up to?
A non-zero number.
Right. And in particular, if the system is accelerating, what's Newton's second law for that? Some of the forces would have to equal what?
The product of mass and acceleration.
Right. Which means if we know the person's mass and we know how much the person is accelerating, we can multiply those to find the total force. Then if we only have one unknown force, we can solve for that unknown force because we know what they have to add up to. So this same situation can be analyzed if it is accelerating, as long as you know how much it's accelerating, the rate of acceleration, and of course the masses of everything in the system. In this case, though, there's no acceleration, so we don't need to worry about that. We can just assume all the forces on each object add up to 0. And in this case, the sum of the forces on the person adding up to 0 tells us the force of the beam on the person has to balance out the force of gravity on the person, which also tells us the force of the person on the beam matches that same gravitational force. It is not a gravitational force, but it has to equal the same strength. Any questions on that so far? And it looks like so far we've got a couple of downward forces on the beam, but the beam isn't falling. So what else has to be acting on the beam to prevent it from falling?
Tension from the rope and then a force from that pivot point, probably.
Yeah, the cable or rope is providing tension at the location where it's attached, and also in which direction.
Pointing towards the direction of the rope.
Yeah, the only thing a rope or cable can do is pull. So a tension force is always in the direction of the rope's pull. And we don't know how strong that is yet, but we at least know the direction. So we'll call that Ft, the force of tension. And we don't know how strong that is. But we at least know the angle it makes. And you mentioned also the pivot point, the hinge where it's attached to the wall. That also provides a force. And we don't really know how strong that force is. And strictly speaking, we don't even know the direction. The exact direction of the force from the pivot point is going to be whatever is necessary to balance out everything else. Because what should all of these forces add up to?
0. So can we technically say we know it's in the direction, like away from the post and up, because the other forces have a negative x and a negative y component?
Well, we do need this force to be to the right to some extent, because we do have the force of tension is to the left, and there's nothing else to the right or to the left. So the only x component so far is to the left. So we've got to have.
But we don't know for up and down.
Right, because we know we've got downward forces from the person and from gravity. We've also got an unknown amount of upward component from tension. So we don't really know how those balance out yet. So I think we're going to have to assume that the only thing we know about the force from the pivot point is it's got a rightwards component. It may also have an upwards or downwards component, but we don't know yet. So I'm just going to leave that entirely unknown. I'm not even going to draw an arrow yet. I'm just going to say force of the, we're already using P for person. Let's say force of the hinge, FH. So force of the hinge, we have no idea. We don't know the direction. We don't know the magnitude. We know it has a positive X component, but we don't know if the Y component is positive or negative or maybe even 0. Any questions on that so far? And it looks like that is all the forces acting on the beam. The question we're actually trying to address here is, how does the tension change, or does it change at all if you move further away on the beam? That is, if we change this force of the person to further out along the beam. We're not changing how strong the force is, but by moving further along the beam, what does change?
The torque.
Yeah, we're changing the torque, yeah, because of the radius changing. If you take this person that's some short distance from the pivot point, like if we actually draw in the radius vector, we've got a small radius vector. But if you move further out along the beam, you're increasing the radius vector. So what would you expect to happen to torque?
Increase.
Right. The person's going to be applying more and more torque. As you move further out along the beam, the same force becomes more effective. It creates more and more torque because of the larger radius. But what should we expect about all the torques acting on the beam?
They add up to 0.
Yeah, there's no rotational acceleration involved here, so we should expect all the torques to add up to 0. So if the person's torque increases because the person's moving further out, longer radius, what's the only other torque that could change here?
The tension?
Yeah, the tension force is, or the torque provided by tension is going to have to increase to match. Because we know gravity is exerting a constant amount of force at a constant location. So the torque from gravity can't change. And what do we know about the torque provided by the hinge?
If we're analyzing that point, wouldn't it be 0?
Right. Any force at the pivot point provides no torque at all. So we've got no torque from the hinge. We've got a constant torque from gravity, because gravity is the same amount of force all the time and the same location all the time. So that tells us if the torque from the person increases, then the torque from the cable what would have to happen to that to balance it out?
Decrease.
if we got an increase in one torque and a decrease in the other torque? Because what do we know about the directions here? How would we actually calculate the direction of each of these torques?
Using the right-hand rule.
Yeah, so using the right-hand rule, what would be the direction of the person's torque?
In.
Yeah, the person's exerting an inwards torque because you can stretch out your hand towards from the pivot point towards the location of the force, then curl in the direction of the force, and your thumb's pointing into the screen or into the page. So we've got, if we add these up, let me actually write out the equation here. 1 moment. And grab a Greek tau. So if we have torque from the person plus torque from gravity plus torque from tension, and we know those have to add up to 0. We know the person is exerting an inwards torque, that is into the screen away from the viewer. So we'll draw that as a circle with an X, representing an arrow pointing away from the viewer. What about the torque from gravity?
Also in.
Right. Because gravity is trying to do the same thing. The gravity and the person's force are both trying to make it rotate. I guess that would be clockwise. And what about the torque from the cable?
Out.
Yeah. Cable is trying to make it rotate the other direction. So that's going to be an outwards torque. So for the cable, we'll draw the arrow pointing towards the viewer, out of the screen.
So then the net must increase because they're in opposite directions.
Right. Because if we have increase in the person's torque due to the increased radius, but we have no change in the gravitational torque, then yeah, the cable torque in the opposite direction also has to increase. That way we've got an increase in the outwards torque and an increase in the inwards torque. Those will balance out to create no change in torque entirely, as long as we increase in them by the same amount. So yeah, it looks like the tension in the rope is going to have to get stronger. And I think this should match up with what we should expect intuitively. That is, as you walk further and further out on the beam, you're pushing in a way that you're pushing with the same force, but further and further out on the beam, the tension is going to need to get stronger to support you. Whereas if you're closer to the wall, then the pivot is going to be doing most of the support. So it looks like further out, as you stand further and further out on the beam, tension is going to have to get stronger and stronger. Any questions on that so far? And in part 2, it tells us that once you reach a certain new location, it tells us what the tension is. So let's move on to part 2. If we know that the tension is 1200 newtons, when you're at some certain location, some new location. So let's say you're now standing right here. Let's say you have moved to this new location. And in the new location, we know you're still exerting a 500 Newton force on the beam, but you're now at some unknown radius. And it doesn't really give us any specific lengths here. It just says we're treating the length of the beam as L, capital L. So the full length of the beam is L. Let me actually mark that separately. The full length of the beam is L. And you're standing at some unknown distance. Let's say that unknown distance is, let's say, capital R. So you're standing some unknown distance, capital R, from the pivot point. And we want to figure out how does that R relate to the total length of the beam L. So our answer here should be something like R equals some fraction of L. And we want to figure out exactly what fraction of L. Any questions on that setup so far? And it looks like we have one equation already. We know that the torques have to add up to 0. So let's see if we can write out those torques as expressions in terms of the forces and distances. For example, for the person, how would you actually calculate torque that the person exerts on the beam? What's our usual expression for
R, like R perpendicular times force, or F perpendicular times R?
Yeah, and there's actually 3 ways you can write it. You can say torque equals the radius times the force, well, sometimes just the perpendicular component of the force. Or you could write it as the force times the perpendicular component of the radius. Or alternatively, I guess what I usually consider the more universal or more general formula is the radius times the force times the sine of the angle between them. Let me go get a theta here. Theta, there it is. So torque is the radius times the force times the sine of the angle between them. But you could also bundle F times sine theta together to create F perpendicular, or you could bundle R times sine theta together to get R perpendicular. In this case, though, what's the angle between the radius and the force?
90.
And what's sine of 90 degrees?
1.
Right. So that means we can essentially ignore the sine theta here and just treat it as R times F. You could also think of it as either of the other 2 formulas, but since the radius and force are completely perpendicular already, F perpendicular is just all of F, and likewise R perpendicular is all of R. So in general, if the radius and force are completely perpendicular already, then the torque is just radius times force, or moment arm times force, I should say. So torque from the person is just going to be this unknown distance R times the force, which we know is 500 newtons. And what about torque from gravity? What's the distance for gravity?
1/2 L.
Right. Since it's the middle of the beam, it'll be half of the length of the beam. So this should be half of L times the force of gravity, 1,000 newtons. And then for the cable, what's the distance?
L.
Right. We've got the full distance L. And for the cable, we're going to have to do things a little differently because this is not perpendicular. For both the person and the gravity, the force is perpendicular to the radius, moment arm. So we just have radius times force times sine of 90, which is 1. But for the cable, there are a few ways we could do this. One way is we could actually just multiply radius times force times sine theta, because we have the radius, we have the force, we have the angle. So I think that'd be the most direct way to do this. Radius times force times sine of the angle. That'll tell you the torque from the cable. Alternatively, you could also split up the force of tension into components. L over 2, yeah, that for gravity, we're multiplying moment arm times force. For gravity, the moment arm, and for any force, the moment arm is the distance from the pivot point to the location where the force is being applied. For gravity, we're going from the moment arm to, make that a little thicker, or from the pivot point to the location where gravity is acting on the beam. But where is gravity acting on the beam?
Center of mass.
Right, which I think we can assume is exactly halfway. Yeah, the problem specifically says it is a uniform beam. Uniform, I would interpret as meaning uniform density. It's the same density everywhere. So the center of mass really is the geometric center of the object. If the density was not uniform, like let's say one end was made of a denser material than the other. So like maybe we have a really dense material here, maybe like one end is made of iron, the other end is made of styrofoam or something. In that case, I'd expect the center of mass to be closer to the denser end. But if the whole beam is made of the same material, same density throughout, then the center of mass will be the geometric center. And the center of mass is always the location where gravity is acting. So since that's exactly in the center, we would assume that it's halfway to the end. So that'll be half of the length of the beam, therefore L over 2. Whereas the tension force is located all the way at the end of the beam. So that will be L away from the pivot point. So L, the full length of the beam for the moment arm, times 1200 newtons for the force, times sine of the angle between them. And by the angle between them, we're talking, you've got the radius vector and the moment arm. So the angle between them is the 30 degrees here. So we'll take sine of 30 degrees, which is 1/2, I believe. Alternatively, we could split the tension force into components. Specifically, a component parallel to the radius and a component perpendicular to the radius. So it's not always splitting into conventional X and Y components. It's not always horizontal and vertical. The important thing is you want to split the force into a component parallel to the radius vector, which in this case is along the beam, and a component perpendicular to the radius vector, or moment arm vector. And the perpendicular component is what we actually care about. But in this triangle, how would you solve for that perpendicular component? How would you solve for this vertical side here?
1200 sine 30.
Right, which is exactly what we get by multiplying F sine theta anyway. Or alternatively, you could keep the force as it is and multiply the perpendicular component of the radius. And for that, you'd keep the force as it is, but you'd split up the radius. Instead of having the radius be this whole thing, you would split up the radius into a component perpendicular to the force and a component parallel to the force. Let me adjust that a little bit. So we're making a right triangle. If we wanted to split up the radius into components, we'd make a right triangle where the hypotenuse is the radius itself. One of the legs is parallel to the force, and the other leg is perpendicular to the force. So in that case, this length would be our perpendicular. In some cases, that's easier to use. In this case, I don't think it will be. We do know the force, but it would be inconvenient to try and measure our perpendicular. We'd have to use trigonometry, and if we're going to use trigonometry anyway, we may as well just use RF sine theta. But if you did want to use our perpendicular, this is how you draw it out, or at least one way to draw it out. You got the actual moment arm, the length of the beam itself, and you draw out a triangle splitting it up into a component perpendicular to the force and a component parallel to the force. So that's what it would look like if you wanted to draw the perpendicular component of the radius. Any questions on that so far? Excuse me. So many ways to do this, but in this case, since we have the radius, at least in terms of the variable L that we're trying to get everything in terms of, and we have the force, 1200 newtons, and we have the angle, we may as well just use RF sine theta. So if we add all these up, they should add up to 0, except how do we decide which ones to call positive and which ones to call negative? Because we certainly can't have a bunch of positive values adding up to 0. At least one of these has to be negative. So how would we decide which ones to call positive versus negative?
Could you just do like torque in equals torque out, and then you wouldn't have to do positive?
That is one way to do it. You could just say the total amount of torque in the inwards direction has to equal the total amount of torque in the outwards direction. Or you could also just choose a sign for each direction. Yeah, let's say out is negative. And yeah, there isn't really a universal standard for one direction being positive and one direction being negative. Generally, what you want to do is just choose one direction to call positive and one direction to call negative. That's true for any pair of directions, by the way. If you're talking about, for instance, up and down, you could call up positive and down negative, or you could call down positive and up negative. we traditionally call upwards the positive direction, but it doesn't have to be. We just need to choose a convention and stick to it throughout the problem. So yeah, let's say we call outwards negative and inwards positive. And we should make a note of that. I would generally recommend, let's say, outwards equals negative and inwards equals positive. Just to make a note on the force diagram or somewhere else in an obviously findable space, both as a reminder to yourself and to whoever else might be reading or grading it later. Which means any force in the outwards direction we'll call negative. Or sorry, any torque in the outwards direction we'll call negative. Any torque in the inwards direction we'll call positive. And as you said, it doesn't really matter which is which. We just want to be consistent about it. So those all have to add up to 0. And of this, what are we actually trying to solve for? What's our goal here? Yeah, we want to find R. Let's simplify things a little bit first. We've got R times 500 newtons plus L over 2 times 1,000 newtons. We can combine the half and the 1,000 to get 500. So L times 500 newtons. And then minus sine 30 degrees is also 1/2. So 1,200 times 1/2 would be 600. And what else could we simplify here? Yeah, 500L minus 600L, those combine to what, minus 100L, 100 newtons times L. And then that's pretty much as simplified as we can get it. What else would we need to do to actually solve for R here? Yeah, add 100L to both sides. So 500 newtons times R equals 100 newtons times L. And then what? Yeah, divide by 500 newtons. So on the left side, those cancel out entirely. On the right side, newtons and newtons cancel out, and we get 100 over 500. So it looks like R is going to be 1/5 times L. So that's the result we were looking for. We've got the moment arm for the person, that is how far the person is from the hinge, written as a fraction of the length of the beam. In order for this to work, in order to get exactly 1,200 newtons of tension force, you've got to be 1/5 of the way along the beam. So for instance, if the beam was 10 meters long, you'd be 2 meters along the beam, or more generally, 1/5 of the length of the beam. Any other questions on that? And while we're at it, we now have the tension and force in the rope. We know where the person is standing. Given that information, what other question do you think we might be able to answer? What's one other piece of information we could find here if we needed to? What's the last big unknown in this free body diagram? Was there any force or distance we hadn't figured out yet? Yeah, the hinge itself. And I would say the force of the hinge rather than the torque of the hinge, because how much torque is the hinge producing? Yeah, the hinge produces 0 torque because it's at the pivot point. Radius would be 0. But it does produce some as yet unknown amount of force. We could now find that force because we know all the other forces, 500 newtons downwards, 1,000 newtons downwards, 1,200 newtons at a 30-degree angle. And what do all these forces have to add up to? Yeah, they all have to add up to 0. In a two-dimensional problem, we can split that forces add up to 0 equation into 2 equations. we can say that the sum of the x components of forces add up to 0, and separately the sum of the y components of forces add up to 0. And in this situation, what are the only forces that even have x components? Yeah, definitely the tension force. So tension force, x component. Person force and gravity force definitely are straight down. They have no x component. But what else at least could have an x component? Right, force of the hinge could have an x component. In fact, it looks like it's going to have to because it has to cancel out the tension force x component. Whereas for the y direction, it looks like everything could have y components. We've got force of the person in the y direction, force of gravity in the y direction, force of tension in the y direction, and force of the hinge in the y direction, adding up to 0. And we know person and gravity are, I guess we would call these negative 500 and negative 1000 because they're in the negative y direction. So those combine to just negative 1500 newtons. We don't know the y component of the hinge, but we could split up force of tension because we're trying to split that up, in this case, into a x component and y component. How would we calculate those x component and y component? If we wanted to know how much of this force is in the x direction and how much is in the y direction, we know the force itself is 1200 newtons. Yeah, we can use Ft sine 30. And note that that's the same F tension sine 30 we use for calculating torque as well, because the y component in this case is F perpendicular. And yeah, cosine 30 for x. So for y component, we've got just Ft sine 30, which we already saw was 600 newtons because sine 30 is 1/2. So the y component, 600 newtons. And the x component, Ft cosine 30. And 1200 times cosine 30, cosine 30 should be root 3 over 2. So that's 1200 times root 3 over 2, which simplifies to 600 times root 3. Also, since that's to the left, how would we designate that? Yeah, we'll call that negative 600 root 3 newtons. So we've got tension x component is negative 600 root 3 newtons plus an unknown x component of the hinge. But it looks like each of these equations, the x component equation and the y component equation, now only has one unknown. So we can solve each of those individually. If they had multiple unknowns, we could probably combine them together as a system of equations. As long as you've got as many equations as you have unknowns, that's a system that can be solved using substitution or elimination or matrix methods. In this case, we could just add 600 root 3 to both sides. So the x component of the hinge force has to be 600 root 3 newtons. And here, simplifying these, it looks like that's negative 900. So we add 900 to both sides. So we now have the x and y components of the hinge force. We know force of the hinge is 600 root 3, comma 900 newtons. That's the x and y components. And how do we turn that into a magnitude and a direction? If we know it's 600 root 3 to the right and 900 up. How would we actually calculate that direction and the magnitude? Yeah, we could use Pythagorean theorem for the magnitude. Leg squared plus leg squared equals hypotenuse squared. So that means the magnitude of the tension force is going to be square root of 600 root 3 squared, so that's 3600 times 3, plus 900 squared. Right, that's not 3600. 3600, and then 8100. So add those up, take the square root, that'll tell you the magnitude. And what about for the direction? How could we find an angle here? Yeah, inverse tangent should work. Inverse tangent of, because tangent of this angle would be opposite over adjacent, that's y component over x component. So we can just take the inverse tangent and say the angle is the inverse tangent or arctangent of y over x. We want to put that in parentheses as well. So 900 over 600 root 3, take the inverse tangent, and that'll tell you the angle, angle of elevation of that force of the hinge. So that's the magnitude, the direction, and that'll tell us everything we need to know about that hinge force, which we could then include on the diagram. And you'll want to draw that to scale, figure out what's the magnitude, and then draw it to scale with the other forces that you've drawn in there. And I think that's everything we would need to know about this beam. And a lot of the reason we want to know this, for instance, maybe the tension can, or the rope can presumably only withstand a certain amount of force before it breaks. So you'd want to calculate in advance what's the tension on the rope, and then make sure you have rope that can withstand that much force. Or maybe we know this rope can only withstand up to 1200 newtons of force safely. So we calculate R, and that tells you how far you can go out on the beam safely before it might break. Likewise, you might also want to find how much force the hinge is going to be experiencing, so you know how strong that hinge needs to be. Any other questions on that? All right, try out some more examples using this same sort of method. Draw out a free body diagram for whatever, or extended free body diagram, I should say, for whatever object or objects seem to be experiencing the most forces that you know and or care about. And as long as the system is not accelerating, you can write out the torques add up to 0 and the forces add up to 0. The forces in a two-dimensional system can be split into x and y components. So as long as you've got as many equations as you have unknown variables, that's a system of equations you can solve. So give that a try. Let me know if you have any other questions, and I will see you next time. You're welcome.